Hello, I'm Matthew Barania, and today my topic is going to be on medicine in the stone world. So this brings us to the question, what if every single human on Earth were to be turned to stone, right? First of all, many bad things could happen. For example, nuclear plant explosions, possibly the flooding of large cities and um, towns, and maybe fires, like forest fires and city fires, and because of that, possibly reverting back to the Dark Ages, right? When dust filled the skies, and possibly even the Ice Age because of it. But even though there's a lot of bad things, what good things come from the disappearance of humans, or in this case, the petrification of humans? First of all, reduce pollution. Now, during this time, during COVID, because not that much people are going outside, or some people are, but most people are staying inside, there actually has been a slight reduction in the amount of pollution in our airs. So imagine that same thing where people are quarantined. Actually, in this case, there's no people. Our CO2 emissions would decrease by a lot over, let's say, thousands of years. Now, another good thing that comes is the wildlife and the nature that grows around, right? Our cities will no longer look like, urban areas will be full of green, right? Trees, wildlife, all different types of bacteria and animals. And also many extinct animals, actually not, maybe not extinct, but many animals would, survive. But today is not going to really be on that. So another question I want to ask you guys is, what if a handful of people were to return to this new world? This new world full of greenery, this new world where wildlife reclaimed the whole earth, right? And what would happen if someone were to get sick? Let's say you got the common cold, but now there's no medication. So there's a chance that you could die from something like the common cold. What if you had pneumonia, right? There's a chance you might die from that. So how do we cure them without the help of the technology that we have today? And the answer to that is medicine. So that video was actually the, I guess, the inspiration for this lesson, or for these lessons, for this topic of a medicine in a stone world. So Senko actually used the power of science to create a medicine to heal someone who is suffering from pneumonia, right? And pneumonia, you might think, is pretty common, actually not that common, but it's pretty easy to heal with the drugs that we have today. But in a world without those drugs, without the technology to make them also, it's very hard to create medicine like that. So at the start of our lesson, we need to know some background info. So in a chemical reaction, the elements and compounds on the left side of the arrow are the reactants, and the elements and compounds on the right side of the arrow are the products. The law of conservation of mass states that in a chemical reaction, the mass of the products is always equal to the mass of the reactants. Meaning, in this reactant of sulfate plus oxygen, right, on the reactant side, it should have the same mass as the product side. Another thing we need to know is everything on Earth is made up of atoms. Atoms are made up of subparticles, which are protons, electrons, and neutrons. Homogeneous mixtures are mixtures which have a composition that is uniform throughout the mixture, for example, apple juice. Heterogeneous mixtures are mixtures which do not have a uniform composition, for example, oil and water. Solutions are homogeneous mixtures between two or more substances. And concentration is the percent of the quantity of a solute divided by the quantity of the solution. Which brings us to my first lesson, which is the types of reactions. So chemical reactions, as we know, are very important to human. For example, when we eat, when we digest our food, and when we use our digested food to get energy from it, right? And another thing is that chemical reactions are very important to medicine, which is our topic, because we need the different products which have different properties. So for the final product, we can use those different products and create the drug. For example, here we have sulfuric acid. And, as we know, sulfuric acid is very dangerous. It can hurt people, right? It's very corrosive, can cause severe skin burns, can irritate the nose and the throat. But if it's used in the right way, it could possibly be part of making a drug to help someone. For example, in the show, we saw that he had sulfuric acid and he used part of sulfuric acid in his process of making the final drug and eventually made something that helped the person cure their pneumonia, right? So what are the different types of reactions? Now we need to know this. So the first type of reaction we have is synthesis, which is A, B, so two separate elements or compounds forming to create one. Now in the opposite way, we have decomposition. Now decomposition is one singular compound or element, actually mostly a compound or molecule, and it's breaking down into separate elements or compounds. Now we have single displacement, where we have a compound or two compounds, I guess, adding together, right? And I guess they switch places. In this case, we see A, B are together and C is by itself. But in the next part, the products, A and C are together and B is by itself. Now in a similar way, double displacement does the same thing. So A and B in this case are together and C and D are together. But when it goes to the product side, A and D are together and C and B are together. So it kind of switches places. I guess the second element switches places with each other. Now we have combustion. So what it says here, it says C, X, H, Y. The X and Y values are, they're variables, right? You can change them around for different numbers, right? So what it is though, it is a hydrocarbon. Now, if you see a hydrocarbon in a chemical equation, it's safe to assume that it's going to be a combustion reaction. Now, it really depends on the products though. So what this is hydrocarbon with oxygen to create carbon dioxide and water. However, what this is a complete combustion reaction. Now, if it was incomplete combustion reaction, it would have carbon and also have carbon monoxide as a product. So the next type of reaction is neutralization. Now this one is basically just an acid and a base reacting together. So if you see an acid and a base reacting together, it is also safe to assume that it's going to be a neutralization reaction. Now, you could argue that, yeah, it's a double displacement reaction. Sometimes it's a double displacement reaction. But once you notice that it is an acid and a base, which creates salt and water, then you can assume that it's a neutralization reaction. So this brings us to the next part of the lesson, which is balancing chemical equations. So in this case, to start balancing chemical equations, we need to first create a skeleton equation. So in this case, we have a combustion reaction because it is a hydrocarbon. It is a hydrocarbon reacting with oxygen to create carbon dioxide and water. So now we have the skeleton equation. Now the step 2 is to count the atoms of each element for the reactants. So let's count the reactants. We have 3 carbons, we have 8 hydrogens, and we have 2 oxygens, right? Now let's count, step 3, let's count the atoms of each element for the products. So the products, we have 1 carbon, we have 2 hydrogens, and looks like we have 3 oxygens. Which brings us to the 4th step. Now, add coefficients, which is the numbers in front of the elements or the compounds, so that both the reactants and the products are the same because of the law of conservation of mass. So let's start off with carbon, right? So we're looking for the greater number. So in this case, reactants has the greater number of carbons. So in this case, it's 3 and 1. Now we're going to look for if the lower number is a factor of the larger number. In this case, it is, because 1 is a factor of 3, meaning we just need to multiply by 3 to get to 3, right? Good. Now, our new products are 3 carbons, 2 hydrogens, and 7 oxygens. Now, one tip that I think we should go over is if you see a element which is by itself, in this case it's O2, then generally you want to balance that last because it just makes it easier for you. And if you were to change this, then it wouldn't really affect the other ones. For example, if I were to change C3H8 and balance this last, it would be harder for me to balance it because it affects so much, because it affects the carbons and affects the hydrogens. So aside from that, let's do the next one. So let's go for hydrogens, right? So the large number is 8, and the small number is 2 on the product side. So 2 is a factor of 8. Good. Now we just need to multiply by 4 to get to 8. Right? Now our new products are 3 carbons, 8 hydrogens, and 10 oxygens. And this is the last step, right? Because carbons and hydrogens are balanced, now we have to balance oxygen. So in this case, the product actually has the greater number of oxygens. So let's go see if a 2 is a factor of 10, in which it is. So we just need to multiply oxygen by 5 to balance the equation. And this is our final balanced equation. For balancing chemical equations is if you see any compounds that are by itself, for example, hydroxide or phosphate, you count them as its own element so that's easier for you to balance, right? Because you could either do the other way by counting it as its own separate element, right? Like adding oxygen to whatever oxygen atoms there are, right? But it's just easier for you to just count this as a whole, as a whole element, right? And balance it on both sides because you have less to count, and it's just really easy, right? Now the second tip is like what I said before, just try to balance the elements that are by itself, like what we just did, like the O2 example. Now, when we're talking about chemical equations, we need to know how those chemical equations come to be, how compounds come together, and which brings us to our lesson of chemical bonding. So chemical bonding is a very crucial part to all life on Earth. For example, water, it wouldn't exist without chemical bonding. Technically, we all wouldn't exist without chemical bonding. So it's very important. Now, this makes chemical bonding important to learn because we should know how atoms are held together. It also helps us to describe the chemical structures in molecules and so chemical bonds are the force of attraction holding atoms together in a compound or molecule. And there's a funny picture over here. Now, the different types of bonds that occur in molecules are ionic bonds. So what ionic bonds are, it's when electrons are transferred from one atom to another. And this usually occurs between metals and nonmetals. So in this example, or in this diagram, we have sodium making an ionic bond with chlorine. In this case, the valence electron, is going to transfer over to the chlorine to make chlorine balanced. And when an atom is balanced, it means it has a full octet, right? And in this case, it loses the electron. For Na, it loses the electron so that it has a full octet, right? And for chlorine, it gains one, so it gets a full octet. So the next type of bond is a covalent bond. So these occur when electrons are shared between atoms, and this usually happens between two nonmetals, right? So in this case, instead of transferring the electron from chlorine to carbon, it actually shares it, right? It's not transferring because it's sharing the electron, so they both have a full octet. And the next type of bond that occurs, which is not really that important to our lesson, but it's important to know, is a metallic bond, which is the sharing of detached electrons between positive ions, and usually happens between metals and metals. So one thing to, I guess, learn from this is that if you see a bond between a metal and a metal, it is very safe to assume that it is a metallic bond. And in this diagram, you see here the um, the electrons are actually further away from the actual atom, and they're not transferring. So it's not like the atoms or the electrons are leaving the zinc atom. It's just sharing them. So it's kind of like a mixture of ionic bonds and covalent bonds. But how would we differentiate between an ionic bond and a covalent bond? And the answer is electronegativity. So electronegativity is the measure of an atom's ability to attract electrons in a chemical bond. So the higher the electronegativity value, the greater attraction it has to electrons, right? So right here, this is just the periodic table, but with electronegativity values. For example, hydrogen has 2.2 as electronegativity, which is less than, let's say, I don't know, oxygen, right? Oxygen has a electronegativity value of 3.4. But these electronegativity values aren't, they vary. So for this periodic table, it could have different values in, let's say, another periodic table. But one thing to note, but this is not really that important to the lesson, but one thing to note is that as you go down the periodic table, electronegativity decreases. And as you go left to right on the periodic table, the electronegativity increases. Use the electronegativity value to determine whether it is a covalent or ionic bond. We have something here called the Electronegativity Scale, right? And what we're doing is we're actually finding the difference between electronegativity values. So right here, we see that a nonpolar covalent bond is when it has electronegativity value less or equal to 0.4. Now, if it's greater than 0.4 and between 0.4 and 1.8, then it is a polar covalent bond. If it's greater than 1.8, then it is an ionic bond. However, these electronegativity scales actually differ, right? They are different in like many types of electronegativity scales, but the values are very similar. So one electronegativity scale could have nonpolar covalent being around, I don't know, 0.3, while another one could have a value of 0.5 or something. So let's do some examples. So in this case, we have oxygen with oxygen. So oxygen actually has electronegativity value of 3.5. And if you have two of them, then they cancel each other out. So 3.5 minus 3.5 is going to equal to 0, meaning that that bond between them is a non-polar covalent bond. Now let's go on to the next one with carbon and oxygen. So we know that oxygen has a electronegativity value of 3.5. And carbon has electronegativity value of 2.5. Now, we're subtracting the larger number by the smaller number, in this case 3.5 minus small number of 2.5, and we get a value of 1, right? And that's between the 0.4 and the 1.8, meaning that this is in fact a polar covalent bond. And going to the next one, we have the ionic bond, right? And this is an example of it. So 3 minus 0.9 is 2.1. And that's greater than 1.8, meaning that it's an ionic bond. But now, excluding the ionic bond, what does it mean for a covalent bond to be polar and nonpolar? And to differentiate between the two, we know about dipoles. So dipoles are the part of a molecule that has a pole, so slightly negative or slightly positive end. In this case, a non-polar covalent bond would not have either, right? It wouldn't have any dipoles because the electronegativity value is so close to each other that electrons wouldn't want to attract near another element than it would another. So electrons would want to attract between this one than this one. But it's different for polar covalent because this atom or this element right here would have a greater electronegativity value than this one, meaning that electrons would want to, I guess, attract towards this atom, making it polar. So that gives it a slightly negative charge and a slightly positive charge. And of course, ionic bonds, if they, I mean, the electronegativity difference is so great that they transfer to another, um, they transfer to the another element. Which brings us to intermolecular forces. So this is, dipoles. So one thing that we need to know is there's two types of forces. Intramolecular forces, which is what we just learned. It's forces are the bonds between or the bonds inside molecules. While in this one, intermolecular forces are the bonds between molecules. Right? It shows in this diagram. Intramolecular attraction or forces is between an element and another element inside a molecule. While intermolecular force is between two separate molecules. So there are three types of intermolecular forces. There's dipole-dipole forces, which is interaction between a positive dipole of one molecule and a negative dipole of another. So in this case, we have hydrogen, we have table salt. Wait, no, we have hydrochloric acid, and it's dipole. So when it wants to attract more towards chlorine, in this case, making it a slightly negative charge, it wants to attract towards a slightly positive hydrogen, right? So this wants to attract to this. Then the next type of intermolecular force is hydrogen bonding, which is basically the same as dipole, except that it's hydrogen interacting or making a bond between either nitrogen, oxygen, or fluorine. One thing to note is that hydrogen bonds are stronger than dipole forces, dipole-dipole forces. And the last type of intermolecular force is the London dispersion force. So this is actually the weakest intermolecular force, and it is a temporary attractive force that results when the electrons in two adjacent atoms occupy positions that make atoms form temporary dipoles, and emphasis on temporary because this is not permanent, right? It's like when electrons for a brief moment in time want to attract towards one side. So in this case, it wants to attract to this side. And because of that, it makes a bond, a temporary bond between the two. This brings us to the third lesson, dissolving in solutions. So solubility, which is the ability to dissolve, is important in medicine because it's important for the drug to be able to dissolve in the stomach so it can enter our bloodstream, right? But what molecular processes occur in the dissolving process? So in water, the dissolving process occurs when water molecules collide with the solute, and the loosely held ions near the edges of the solute are attracted to the water molecules because of the slightly charged dipoles, right? So in this example, the water molecules are colliding with this huge solute right here, right? And when it collides, there's a chance that the solute actually bonds with multiple water molecules. In this case, it's right here. And now it's surrounded. But in the opposite way, when water molecules which have solute collide with the main solute, the ions which are bonded with the water molecule can separate and attract to the main solute, which is literally the opposite. It's like when it recollides, I guess, into the solute, the main solute, will attract the solute inside that's surrounded by the water molecule. And this is called crystallization. The last one, which is dissolving, is actually called dissolution. But what factors affect solubility? So the factor one is temperature. So if you were to increase the temperature of the solution, the particles inside would move faster, resulting in the main solute separating and result in the bonding of more solute ions with the water molecules. As you can see, this is salt going into boiling water. And another factor is kinetic energy. By increasing the kinetic energy of the solution, the solute ions would separate from the main solute and eventually the bonds with the water molecules, right? And that brings us to the consolidation. So some lesson one example problems are, the what types of reactions are the following. And I'm going to give you a few seconds. So just pause the video and try to solve all of these questions. I'm going to assume that you just paused, right? So the answer to these questions are following. This is a decomposition reaction because as we remember, this, which is the AB in this scenario, forms from the adding of these two, meaning that in the opposite way, this is actually separating, meaning that's decomposition. Now let's call this A and this is, BC. Looks like A, C are together and B is by itself. And again, decomposition, we talked about that. Synthesis, yeah, two elements are adding to become one. Neutralization, we learned this. This is a acid and this is a base, creating a water and a salt, meaning that this is in fact neutralization. And combustion, we see that this is actually a hydrocarbon which is reacting with oxygen to create carbon dioxide and water. A bonus question is, what type of combustion is this? I'll give you a few seconds. So this type of combustion is actually a complete combustion reaction because it doesn't have any more products, it's just carbon dioxide and water. Now the second type of problem is balance the following equation if it's not already balanced. So I'm going to give you some time, so just pause the video and solve these. I'm going to assume you just paused or you just solved them. So the answer to these questions are the following, right? Let's do one together, right? So as we see here, we have KClO3 and we have one potassium on this side, we have one potassium on this side, we have one chlorine on this side, one chlorine, and we have two oxygens as opposed to three. Now, in this case, let's do oxygens first. So oxygens on this side is 3 on the reactant side, and oxygens on the product side is 2. Now, 2 isn't a factor of 3. So what we can do is just multiply it by 2, right? So we multiply KClO3 by 2, and we did it right here. And now this becomes 6. Now to balance on both sides, 6, right? So there's 2 oxygens, and 2 is a factor of 6, so we just need to multiply by 3, and we did it here. Now how does that affect the other two, right? So now we have 2 potassiums and 2 chlorines. Now let's do chlorine first. So now there's 2 here, and there's 1 on product side. So 1 is a factor of 2, we just need to multiply by 2, and that actually solves both sides. So the final equation is 2KClO3 becomes 2KCl plus 3O2. And the rest is, I guess, self-explanatory. So lesson 2, example problems. What type of bonds are the following? And I'm going to give you some time, so just pause the video. I assume you just paused it, or you just unpaused it. So the answer to the following are polar covalent, ionic bond, non-polar covalent bond, metallic bond. Okay, so this right here is important to note. As we see, zinc is a metal, And because zinc is bonding with another zinc, it's a metallic bond, right? And that's why I said, just assume if it's a metal and a metal, it's going to be a metallic bond. Now, let's go over another one. So let's go over CO2. So carbon actually has electronegativity value of 2.5. And oxygen has electronegativity value of 3.5. So find the difference between them. It is equal to 1. And on the electronegativity scale, if it's greater than 0.4, that means it is a polar covalent bond. And that's the answer. Another example here is O2, right? And something to note is because it's a nonmetal, right? This is actually a gas. We see that there's two of them, meaning that if you find the electronegativity difference, it's going to be 0 because it's going to be, let's say, in this case, oxygen has a electronegativity value of 3.5, and 2.5 minus 3.5 is 0. And that's it. Another example problem is to order the intermolecular forces from strongest to weakest. And I'm going to give you some time. So just pause the video and try to figure out yourself. I assume you just unpaused. So the answer to this is hydrogen bonds are the strongest, dipole forces are the second strongest, and London dispersion forces are the weakest. And I said that in the lesson. Now, lesson 3. Let's say you had two glasses full of water. One of them was cold while the other one was hot. If you were to put the same quantity of salt in both glasses, which glass would dissolve the salt the quickest? And this is a pretty long answer, so I'll give you a bit more time. Just pause the video. I assume you just unpaused. So the answer would be the glass full of hot water would dissolve the salt quicker because the greater the temperature, the quicker the particles in the glass would move. This increases the collision rate between the water molecules and the solute, increasing the rate at which they bond, thus dissolving the salt quicker. Now another question is, if you had a glass full of cold water and put salt in it, how would you decrease the time it took for the salt to dissolve? And as you notice, this is a communication worth 2 marks. So you need to explain 2 concepts. Just pause the video. I assume you just unpaused. So the answer is, to decrease the time it would take for salt to dissolve, you could do 2 things. Increase the temperature by maybe pouring the solution into a pot and boiling it, or stir the glass. By stirring the glass, you increase the kinetic energy in the same way as increasing the temperature. The particle moves faster and collide more, causing the bonding of water molecules and salt to increase and decreasing the time it would take to dissolve. And these are just the citations. So thank you for listening to my lesson. I hope you learned something and hope it taught you more about the different topics and our topic of medicine in the stone world and what we could learn about it.